Bismillahirrahmanirrahim. Assalamu alaikum. So we will discuss now extreme value theorem, and in particular we will prove the extreme value theorem. Extreme value theorem, it is famous in your calculus 1, extreme value theorem. So it basically pertains to, in other words, it is related to continuity of function and compactness of the domain. So it says that if we have a real valued function, let f be a real valued function, let f be a real valued function. So it says that then if f is continuous on the closed interval a and b, then it attains both maximum and minimum. Then it attains its maximum and minimum, minimum on the interval, minimum values on the interval a to b, right? Close interval a to b. So let me break down this theorem into two parts. So if I say my statement p is f is continuous on a to b, and my q is the statement which says that f attains max on this interval, and let me say that my r is the statement which says that f attains minimum on this interval a to b. So I can I can rewrite this statement of the theorem into logical equivalences, in other words into logical language. So it says that p implies q and r, and you already know that this is equivalent to p implies q and p implies r. So if I'm lucky enough to prove this one separately and this one separately, so these both will be true, right? So I will prove this one, and you can, on the same lines, you can prove this one, and that way you will have p implies q and p implies r, and consequently you can say that p implies both p, q and r. So p implies q in this case is going to be that if f is continuous on my closed interval a to b, then it attains maximum. So I'm going to prove for the case of maximum. Then it attains maximum value on the interval a to b, right? And for proving this, we will adopt the strategy of boundedness theorem we will use, and we will also use contradiction principle of proving. So let's start the proof. Okay, so because f is continuous on closed interval a to b, so it is bounded by boundedness theorem. So it must be bounded. So it is bounded, right? Bounded means there is some number m. Okay, let's say there is some number k such that f of x is less than equal to k for all x in the interval a to b. So this is the definition of boundedness. And of course, so basically the set of outputs is bounded, right? Because f is continuous, so it is bounded. And if of we have a set which is bounded in R, so it has to have least upper bound. So suppose m is the least upper bound, for least upper bound for f. When I say f, I mean the set of values of outputs of f of x, right? So if there is c if there exists C in the interval a to b such that f of c is m, then nothing to prove. Then we are done, right? So if this is the case, because this is the least upper bound, and if it is attended on some value c in the interval, then this is going to be the value which is largest of all the outputs. So if this is the case, then we are done. Suppose contrary that this is not the case. So suppose contrary, suppose there is no such c. Suppose there is no such c in the interval a to b such that f of c is equal to m. So we are assuming that there is no any c. If this is the case, that means f of x on all values in this interval has to be less than m for all values of x in the interval a to b, because we have no any c where this f of c is m, and m is the least upper bound of the outputs. So for every you know input, the f of x has the value which should be less than m, right? Let's define a new function g of x, which is given by 1 over m minus f of x, right? So then, because m minus f is less than m, so this implies that m minus f has to be positive. So in other words, this function g of x has to be positive for all values of x in the interval a to b, right? And furthermore, we also see that g is continuous. Why? Because only discontinuity that could arise was f of x to be m on this interval a to b, and we have assumed that there is no such c where this should happen. So like this is not the possibility. In other words, the denominator can never vanish. So you can say that for the values of x in the interval a to b, and this way you can say that g of x is continuous on the interval a to b, right? Because g is continuous on this closed interval, so it has to be bounded. So g of x is bounded again by same boundedness theorem. G of x is bounded because g of x is bounded, so it must also have some what should I say, least upper bound. So let k be the least upper bound, be the least upper bound for my g of x. So I can say that g of x, what can we say, that g of x must be less than equal to k for all x values in the interval a to b, because g is bounded by k. So, k is the least upper bound. Consequently, we can say that 1 over m minus f of x, just substituting the value of g of x, is less than equal to k. And because this number m minus f of x, this number is positive, so I can write this in another form, uh, which is 1 less than equal to k times m minus f of x, or I can write it 1 over k less than equal to m minus f of x, or even I can rearrange it to write f of x less than equal to m minus 1 over k, right? So this means either 1 over k is less than, oh sorry, control, so like I have written over here something. So I have written f of x less than equal to m minus 1 over k, and this means either my f of x is less than m minus 1 over k, or or f of x is equal to m minus 1 over k, right? So either this is true or this is true. We'll explain this in this way, right? So like suppose this is a and this is b, so this is my interval, let's say, right? And let's say here I have got my m, right? So this is m, and when you are subtracting 1 over k from m, so it is somewhere like here, m minus 1 over k. You have already said that my all values of f can either be equal to m or less than, because it is the least upper bound. But you are again saying that there is another number m minus 1 over k So f of x is also less than the m minus 1 over k, which is not possible, because if this is the case, then this will become a new candidate for the least upper bound, right? Same argument, so you can give over here, and you can say that this contradicts with the assumption of m being least upper bound. So this f of x less than equal to m minus 1 over k contradicts the assumption of m being the least upper bound, because we have in other words, we have got another potential candidate for least upper bound, which cannot be the case. Hence we can say that our assumption is the you can say that m was the least upper bound, so this can't happen, and that leaves the only possibility that there is c in the interval. So because this contradicts the assumption, hence there exists c in the interval a to b, such that f of c is equal to m. In other words, we have maximum on the interval a to b, right? So let me give the sketch of the proof again. So you had a function continuous on the interval a to b, and because this is continuous, so we had said that this is bounded, right? So we assume that if this is bounded, then it has to be less than equal to some upper bound, and we then tried to say that the least upper bound is in fact achieved on this interval a to b. We assume this, and we said that suppose this is not the case, and we got a contradiction, hence this is going to be the case. So thank you.